I will start with the most conservative assumption. Let us imagine that the interstellar object 3I Atlas is an ordinary natural comet. Based on this, I will try to deduce its properties using the most recent post-perihelion images. In the image of 3I Atlas from November 9, 2029, several jets emanating from the object are clearly visible, extending approximately 1 million kilometers towards the Sun and about 3 million kilometers in the opposite direction. These structures were discussed in detail in the aforementioned report. If the object is an ordinary comet, the expected gas ejection velocity in the jets should be around 0.4 km/s. This is approximately the speed of sound for a rarefied gas at the distance from the Sun where 3I Atlas was traveling. At this velocity, the jets would have had to form and be sustained for several weeks, roughly 1 to 3 months, since the solar wind confines the jets in the sunward direction at a distance of 1 million kilometers. I estimated their mass. Under these conditions, the density is several million proton masses per cubic centimeter at a distance of 1 million kilometers from the center of 3I Atlas. Multiplying the density by the ejection velocity gives a mass flow rate on the order of 5 billion tons per month for an area, corresponding to a square with a side length of 1 million kilometers. Previously, based on the object's early dynamics, I estimated the minimum total mass of 3I Atlas to be 33 billion tons. If we assume that the effective surface area of material involved in the jets is close to 1 million square kilometers, it follows that the object could have lost about 16% of its mass. This value correlates with the mass fraction required to explain its non-gravitational acceleration at perihelion. As shown in my calculations, sublimation of CO2 requires about 600 JPG, and water requires significantly more, 2835 JG, Webb spectroscopy, showed with 3I Atlas at 2.4 times the perihelion distance that about 87% of the gas coma mass was CO2. To supply 5 billion tons of CO2 over a 1-month perihelion period, approximately 3x1018 J of energy is required for sublimation alone. At perihelion orbit, the solar energy flux is 700 J m2 This implies a minimum absorbing surface area of about 4,600 kilometers, equivalent to a sphere with a diameter of 23 kilometers. For comparison, the maximum allowable diameter derived from Hubble images, based on data from July 21st, 2025, is only 5.6 kilometers. If the primary source of ice were water, the required diameter would increase to 51 kilometers. In other words, under the natural comet hypothesis, a clear discrepancy arises. The required surface area to explain the observed mass loss based on the latest image is at least a second times greater than the upper limit established by the Hubble image from July 24, 25, when Webb observed the object on August 6, 2025. The mass loss rate was about 150 kJs. According to the estimate above, at perihelion, it increased to 106 kJs, that is, by 4 orders of magnitude. Such a jump implies an extremely steep power law dependence of mass loss on heliocentric distance, with an exponent on the order of 10.5, which is consistent with the rapid brightening of 3I Atlas at perihelion recorded in observations. The massive outburst and intense brightening at perihelion naturally suggests the object's disruption. Fragmentation drastically increases the total surface area of the material. The area-to-mass ratio is inversely proportional to the characteristic radius of the fragments. To increase the area by at least a factor of 16, 3I Atlas would have had to break apart into at least 16 equal parts, and likely into a much larger number of fragments. This would mean a virtual explosion of the object near the Sun and the fireworks display we are now observing. Thus, if we proceed from the assumption of a natural comet, the latest images testify to its severe disruption under the influence of solar heating. The Sun's further gravitational pull should disperse the fragments over distances in the coming weeks, creating a visual spectacle reminiscent of the fragmentation of Comet, Shoemaker-Levy 9 near Jupiter in 1994. I discussed this possibility a month ago if subsequent observations show that 3I Atlas has, in fact, maintained its integrity and remains a single body. We will have to seriously reconsider the natural hypothesis and contemplate a different origin for the object. The closest approach to Earth will occur on December 19th, 2025, at which point ground-based telescopes, as well as Hubble and Webb, will be able to thoroughly check whether a central nucleus remains or if the object has truly dispersed into numerous fragments. Separately, I note another anomaly I pointed out in an earlier work. The mass of 3I Atlas turned out to be more than 1 million times greater than the mass of 1I Oumuamua. Why did we first detect such a giant, while objects the size of Oumuamua should have been detected significantly more often? According to my estimates, under standard assumptions about the distribution of material in interstellar space, the probability of encountering such an icy giant object near the Sun within a decade is incredibly small. an event rate of once in 10,000 years or rarer. Even under alternative assumptions, the probability drops to almost zero, less than 0.1%, and even lower in other scenarios. Given that 3I Atlas's trajectory is retrograde and, moreover, aligned with the ecliptic plane within Phi Order, the overall probability of a natural origin based on these characteristics alone tends towards 1 in hundreds of millions. If we allow that, the jets are not the result of ice sublimation but originate from engines. The requirement for mass flow changes radically. Chemical rocket engines provide an exhaust velocity of 3 to over 5 km/s, an order of magnitude higher than the expected velocity of natural volatile components. Ion engines are even more efficient, 10-50 km/s. If we are dealing with technological propellants, including hypothetical alien engines with even higher exhaust velocities, then orders of magnitude less fuel mass would be needed to create the observed jets, perhaps only a small fraction of the spacecraft's mass. Upcoming spectroscopic observations will allow us to measure the exhaust velocity, mass flow rate, and composition of the jets, and this is the key to solving the puzzle. Thus, under the assumption of a natural cometary nature for 3I Atlas, the latest post-perihelion images present us with serious contradictions. A disproportionately large surface area required to explain the mass loss, a giant spike in mass loss at perihelion, and an extremely low a priori probability of such a massive interstellar object appearing near the Sun. Either we are observing a comet that disintegrated and shattered into numerous fragments at perihelion, or we are faced with something different, from a classic comet, perhaps even of artificial origin. The next observations, especially closer to the Earth, approach on December 19, 2025, should bring clarity. Will 3I Atlas remain a single body or break into many fragments? Furthermore, spectroscopy will help determine the composition of the jets and the exhaust velocities. Precisely this data will allow us to take a decisive step between the natural and technological hypotheses. Stay curious and keep a close watch on the new observations.